In this lesson, we'll look at annuities and future value. And what we've looked at before is we looked at the time machine. So just as a little prep here, we had a principal and it grew to an amount over a time period. And we had three types of ways it could grow. It could grow simple interest. It could grow by compound interest. 1 plus R over N to the NT, I think. That's the one I used. And then it could grow continuously. But now we're going to look at something new, where we have a series of payments. And at the end of, say, time goes left to right, of course. And at the end of the time, we have what we call the future value. Or I like to call it the big pot of money. So it's a lot of money in there. After all the time, we get the money. Also, this is a future value. You could have a present value. So present value is where you have a big pot of money at the beginning. We call it the present value. And then you make a series of payments to pay back that money. And so this is time going that way again. So these two were the future value and the present value. So future value would be like if you're saving money for something, like you're making a $100 a month payment so that in 18 years your child or niece or nephew or something can go to college and they'll have a pot of money at that time. A present value would be you get a mortgage for a house. And so the bank gives you a pot of money up front and then you pay it back over a series of payments. And we call those annuities. And by annuities, I mean in the mathematical sense, things that you make payments and they have a pot of money at the beginning or ending. There are other types of annuities. A lot of banks and companies that are like insurance companies sell annuities of different flavors and they call them annuities. But I'm just going with the general description here. So if you really get into finance, they'll show you all the flavors of annuities, and the particular company you work for will show you what may have certain names for things that are called types of annuities or whatever. But we're going to keep it simple. Okay, so you could buy a bond and watch it grow. So like you might buy a bond from a bank or a company. That's just where you loan them money and you watch it grow, and it would have compound interest. So you'd give them an amount of money, like say $1,000 and or $100, and over time it'll grow. So let's say it was at, in this case, you could see here's the equation for that. It's this case, compound interest. So you can see it's a 3% growth rate or 3% interest on the bond. And 12, that tells us that it's monthly compounding. And then 5 years. And then this was the principal here. So you can see that it's this equation we're using for a regular bond. That's how it grows. But sometimes you want to make periodic investments or payments. So in this case, we'll be buying $100 a month. So it's like buying a $100 bond every month and then watching each one grow separately. And then you're also watching the pot of money fill as it goes. And we call that an annuity. So suppose we invest $100 per month into an account that pays 5% compounded monthly. And let's watch it grow. So every month we're going to invest $100. So for 6 months. So 1, 2, 3, 4, 5, 6 months. That's our time period. 2, 3, 4, 5, 6. And at the first one, we're going to put $100 in. And so that's going to give us 1, 2, 3, 4, 5 compounds. Do you see that? Because it'll at the end of the month, we'll get one there at the end of this month. So 5. And you can see if you look here, there's that $100 for month 1. And then there's the 5% and 12. But there's the 5 compounds. And then in month 2, so this may be January, February, March, April, May, June. So month 2, if you start in February, how many times will that one compound? Well, you put $100 in there. That one's just going to go 1, 2, 3, 4 times. So you can see a 4 there. And then the one for March, February. This is February, March, April, May. So, and then the last one on month 6, it doesn't have any time to grow. So it doesn't actually grow. So if we added all these together, it's just a big plus sign. Add all those together, that's the value of our annuity at the end of 6 months. And so I call that the sum. So the sum is this first one plus the second one. So I just wrote it out here, and I put ... for all the ones in there. Now let's suppose that I do something crazy here. This is a weird proof technique that I multiply both sides by that. So I have, 1 plus 0.05 over 12 times sum, that's the left side. And then we do that on each one here. So this first one, I have this, 12, and it was to the 5th power, but I multiply again by this. So it'll be to the 6th power. So each of these things I'm underlining, that's the distributive property. And so, and then this one will be the same thing. And it was to the 4th power, so I multiply again, it'll be the 5th power. So it's 5 of them now. And all the way down, and then the 100 will have, again, this thing on it now, which may just look ridiculous. However, if I now look at these two equations and I subtract the first one and add it to this one. So on this left side, I'll have 1 plus 0.05 over 12 times sum. That's this. And then minus sum, because I'm subtracting the top. And then on this next one, you can see there's a to the 6th power. There's nothing to the 6th power there. So I'll just write that. Over 12 to the 6th. And then, but the 5th power, see there's 1 to the 5th and 5th there. So when I subtract it, they go away. There'll be 1 to the 4th in there that'll kill that one. And then all the way down to this one will be in there. And then we'll just have that minus 100. And if it's not making a lot of sense, don't worry about it. This is just a really cool proof. And we'll be using the formula directly when we get to it here in a minute. But I just wanted to show you at least one proof throughout this course. I always have one thing like this I geek out in math, if you're wondering. And this is it. So now I can factor that sum out of there. So I'll have 1 plus 0.05 over 12 minus 1, right? Because there's this and then minus just a 1. If you multiply this out, you'll see it's the same thing as the top. And then this I can factor the 100 out of there. So 100 times 1 plus 0.05 over 12 to the 6th minus 1. So now, if I think about this, the 1's go away. And I really just have sum times 0.05 over 12. And over here I have 100 times whatever that stuff. I'm just taking another chance to simplify it a little. There's no way to simplify this. I know you'll be tempted, but there's no way to get that. There's no way to get this minus 1 inside the parentheses here. You'd have to multiply that out first. You can work it on a calculator, but that's not going to help us. So then divide both sides by this thing. Sum equals. We have 100 times, let's see, on the top, we'll have 1 plus 0.05 over 12 to the 6th minus 1. And underneath it, we'll have 0.05 over 12. So you can see that I'm dividing by this over here. And that is probably written out, typed on the next page. If I know myself, there it is. So that's this. Well, I left the 100s in there, but you could factor the 100s out. You could just say, oh, it's 100 times 1 plus 0.05 over 12 to the 6th minus 1. So I can do this 0.05 over 12. Okay, so what is this 0.05 over 12? We call it I. So I is always going to be the rate divided by 12. And then we call the sum the future value. That's the adding of all this stuff. So whenever I say sum, I really just mean the future value in this case. And so here's our formula right here. This is the big formula. The formula. We will always assume monthly compounding and also monthly payments. So if you want to get a little more complicated, like pay every other month or compound daily, that's fine, but you're not going to see a huge difference in most cases. So you might just, we're just going to go with monthly, and then we'll talk about that a little more later. But just to keep it simple in the formulas and just to have one. And N is the total number of months now, not compounds per year, but months. So I is always R divided by 12, and there we go. So Jack invests $200 per month in an account that pays 7% interest compounded monthly. How much does he have after 10 years? Is it an annuity problem? Well, see how it's per month. That tells us that there's a lot of payments. And that means annuity. So yes, it's an annuity problem. And how do we know? That's the picture. So what's the formula? Oh yeah. Payment 1 plus I to the n minus 1 over I. So what's the future value? That's what we want. The payment we know is 200. N is always 12 times the years. So in this case, 120. It's the total number of payments. It's defined differently than in the other formula we had. And then I is R over N. So in this case, R is 0.07 and N is always going to be, I'm sorry, R over 12. It's always going to be over 12. So 0.07 over 12. You grab the calculator here. It's 0.00583. So 0.00583. And then this says to solve. So all right, let's try it. So future value is, usually I like to put brackets around this nonsense over here. So 200, let's just put all the stuff in. 1 plus 0.00583. I did to the 120 minus 1 over 0.00583. So solving for I first can be a good idea. You can also leave it all in the calculator and I'll know the right answer. So if you do that, you'll have a more accurate answer. So the future value in this case is 200 times, and then that's 1.00583 to the 120th power minus 1 over 0.00583. So you'll be tempted sometimes to subtract that 1. You have to raise to the power first, then subtract the 1. And so what is that? Future value is 200 times, I'm going to do that, 1.00583 to the power. I'm estimating in the calculator is 1.00583 and then raising to the 120 power. So you may have a slightly different answer if you left it on the calc. That's great. 2.00886. And then this stuff. And this is all on one side of the equation, so I'm just going to continue solving it down. So subtract the 1 from the top, you get 1.00886 over 0.00583. And then let's go ahead and divide those two. So we have 200 times what we call the multiplier. So again, I'm going to 1.00886 divided by 0.00583. And by O, I mean 0. And we have 173.046. And multiply those two. So 200 times 173.046. So you may be off by $1 or something, but you'll get the general amount, 34,609.20. So after 10 years, at 7%, 200 a month grows to $34,000, which is a lot of money. And you might say, well, how much of that was interest? And you say, well, how much did you put in? You put 120 payments of 200, which is, I want to say 24,000. But I don't trust myself, so I'm going to use a calculator. 24,000. All right, so 24,000. So basically $10,000 in interest by making those payments along the line. Of course, we did have to find 7% interest rate, and that's pretty close to the average interest rate on a S&P 500 bond. Okay, so the answer is 34,609.20, and again, you may be off a little bit from this because I did have some rounding error here on the I, right there. So rounding error. There's a little bit of rounding error here when I raised it to the power, and I rounded just to 5 decimal places. And then here when I divided, I rounded to 3 decimal places, and then I got down to 2 decimal places there. So yeah, 610, 609. All right, and then let's try another one. How much does Denise need to put in an account each month? So again, each month, that says annuity. So to have 5,006 years. So we have payments, and then there'll be $5,000. So here the future value is what we're interested in, but we don't know how much the payments are. Those are question marks, supposedly. So let's try that. Well, we need our little formula. Let's go ahead and do that. So future value is the payment times 1 plus I over to the n power minus 1 over I. And then we need these things, future value, payment, n, I. Let's do it. All right, so future value we know is 5,000. Payment, that's what we want. The n is going to be 12 because it's monthly times 6 years, so 72. And then the I is R over 12. So it'll be 0.135 over 12, which is, I'll grab the calculator here, 0.135 divided by 12. 0.01125. Just 1 0 this time. Okay, so let's plug in. We have 5,000 equals payment, we don't know, times 1.01125 to the 72 minus 1 all over 0.01125. So you can see that I added the I and the 1 together. So if I is that, then 1 plus I is 1.01125. That might help a little bit if you're like, how do you get that? I just always put that in there. Keeps me from doing something silly like subtracting, like canceling these ones out. That would be a silly thing to do. So just go ahead and do that right there. And then let's continue with this. So 5,000 is the payment times, and then I'll just raise that to the power. First I have to engage the calculator. So 1.01125 to the 72nd power. It's a little calculator exercise here for you. Is 2.23777 minus 1. So I don't always write this many steps in, but let's go ahead on this one. So we have 5,000 equals payment times, and then subtract 1.23777 over 0.01125. So 5,000 is payment times, getting close, I can taste it. So 1.23777 divided by 0.01125, 110.024. And then divide those out. So the payment is going to be 5,000 divided by 110. And so what do we have for the payment? All those steps. 5,000 divided by 110.024 is 45.444. 45.44. So to have $5,000 in 6 years, you just make about $50 a month payments. It's pretty amazing if you think about it. And if you end up in a sales job somewhere, you could say, well, you know, for 5 and 6 years, you know, it's $50 per month to get $5,000. So what if you wanted $10,000? Well, we doubled it. So double this, it'd be $100 a month. What if you wanted $20,000? Then you double this one, so $200. What if you wanted 100,000? So you can kind of figure it out in sales, a little chart. And so this times 10, so maybe $1,000 a month. So you get the idea of how that's at this rate of savings. You can make a little chart for the future. The answer for this problem is 4544, but it's one of the things people do sometimes when they're trying to sell. All right, let's try this one. Julie put $60 per month in an account that pays 17% compounded daily. So again, that's obviously an annuity because of the keywords per month. Not compounded per month, payments per month. So we've got a series of payments happening. And then the money's after 8 years, so it's a future value. There's 8 years. But it's compounded daily. And so you say, oh, we have to have everything compounded monthly and payments monthly to work on our formula. So you kind of have three choices. I like this first one. Just use that our little formula to estimate it. And that'll be close enough for making pound cake. Second one here, look up a formula Wikipedia. Yeah, that's not going to be fun, but you can do it. You can also make a formula in a spreadsheet and just like have for every day or whatever. That's a lot of lines in there. And you're still going to be $1 or $2 off because rounding. And then you can also put the rate into per month terms. Some books show this. So I put it in here just to let you know if you take an economics class or finance class after me and they just, geek out on this stuff. And I don't. I just wanted you to use the one formula and say, that's pretty close. $50 a month, like the last one, at that rate for this. Okay, so answer one's good. And usually if you're someplace working, like a bank or something, they're not going to trust you to figure it anyway. They'll have a computer, you just enter stuff in, it does it. There are websites that do that. So let's do the one other case. So remember in our formula, which was this. More or less. We solved for payment and we solved for future value in two problems. We can also solve for n. So let's try that. $10 per month in an account for some time. So $10 per month is the payments. So this is an annuity because they're making payments every month. And then the account paid 9%. There's a rate, compounded monthly, pretty much no matter what. We're going to assume compounded monthly. If there's now this much in the account, how long? So now we want to know how long. We know the payment's $10 a month now. Let's figure it out. So we have our little thing here, future value payment, I and N. So the future value we know is 22,165.15. The payment's 10. That's not a very big payment. And then that ought to take a while, right? And then the I is R over 12. So that's 0.09 over 12. I grab the calculator here. I get 0.0075. That's a nice number. And N is always the number of compounds. So it's 12 compounds per year times we don't know. So we just say we want N. All right, and then our little formula, future value is payment. I'm just going to write it out because why not? Helps remember. Got to be a little careful with this guy. And then put in this stuff. So 22,165.15 is 10 times all this stuff. 1.0075 to the N. We don't know what N is. Minus 1 over 0.0075. So notice that this minus 1 is not up with the N. It's on the bottom. All right, so now divide both sides by 10. So 22,160 or 2216.515. Right, we divide it by 10. And then we have this thing, 1.0075 to the N minus 1 over 0.0075. Then we multiply both sides by 0.0075. And on the right side, we'll just be left with this little gem. And then on the left side, I have to do that. So 0.0075 times 2216.515 is 16.62 something or other. 16.62, I don't know, 39. Looks good. Add 1 to both sides. So 17.6239 is, like this. Add 1. And those go away. And then we're coming back up here. And then we say, what? How do we get that N out of there? The base. Remember that? Base is 1.0075. So we take the log base 1.0075 both sides. If you don't remember that. So log base 1.0075 of 17.6239 is, and then on this right side, when you take the log of it, you just have N. And now we use a change of base formula. So we have natural log of 17.6239 over natural log of 1.0075. And now we can figure it out with the calculator. So 17.6239 natural log. And then divide that by 1.0075, the natural log of 1.0075. And we get 384, almost exactly. So 384 months. And most humans don't think of months that big, so you divide by 12, and you'd get the number of years. 384 divided by 12 is 32 years. Okay, so you can figure out how long. If you think about it, that's kind of cool. Like $10 a month. I mean, that's $2.50 a week. That's less than a coffee, right? $2.50 a week, 50 cents a day. Every day you work, 50 cents. Just put it in a jar, except maybe not a jar. Something that gets 9% interest, and that's a difference. So what if you did that? You put $10 a month in for 32 years in a jar with no interest. What would you have? You would have put in $10 per month, and how many months? 384. So that would be 3840. So the secret here was time. The 32 years of interest is what gave us that big multiplier of 16 over here. And we only put in less than $4,000 and ended up with 20 at $10 a month. So something to think about there. All right, so you can solve for any of those three things, future value, payment, or N. Payment periods and compound periods will be the same in our examples. That means months. In real life, of course, the interest rates do have a much greater effect than compounding monthly versus daily. So that really means that, like, if your interest rate is 5% versus 3%, that is a much bigger thing than changing the compounding from monthly to daily, right? So over years of an annuity, the interest rate will make a much bigger difference than the compounding. And then what about a mortgage? We'll do that on the next lesson, but you'll see we're going to use the same trick and a similar formula. And then here in the present value, we'll have the pot of present value has the pot of money at the beginning, and then you pay them payments back. And in the future value, you make payments, and then you have the pot of money. So there you go. End of the lesson.